intro, and thank you to all the organizers for putting this together. So I'm Kevin Ellis from Cornell. I'll be talking about work with my students, Tapriya Kulji and Cassidy Langenfeld. So let's get started. So I'll be talking about two things. One is on the human side. I'll be talking about a combinational model of how we learn concepts and categories from a few examples. And a key part of this model is going to be an LLM. And so you're also going to be learning kind of like tech. You're going to be learning tech for using LLMs to be better few-shot learners, and also using them to do better active inference, better experimentation. So to begin, in the first part, I want to just define the problem statement and outline how people have thought about it in the past. So at high level, we're trying to do inductive learning, so generating explicit hypotheses from concrete examples. And our goal is typically to generalize to some held-out test examples. And we want to do this in ways that are efficient, both computationally and also statistically, and also highly flexible, subject to the caveat that we're going to look at learning only from few examples. And we're going to look at these symbolic, discrete, low-dimensional problems, think concepts and categories. So what we mean by efficient is going to be a couple things. One is we want to learn from a few examples. So we probably want like a good prior. And we also want to be flexible, meaning we can learn infinitely many diverse concepts. And for that, what we mean by hypothesis has to be very broad. So we need an expressive hypothesis class. There's a second notion of flexibility, which is more about how much time or compute you spend as an implementation of the learning algorithm. And unfortunately, being efficient in that sense trades off against flexibility. So to better understand that trade-off, we're going to cartoon the problem like this, where there's some hidden hypothesis that generates the data, and we're trying to infer what that hypothesis was. So naively, the most basic way of doing this is some kind of search or optimization. And if our hypotheses are really flexible, it's going to be hard to search over that broad space of hypotheses. Yet, if you look at what humans are able to learn, it's incredibly diverse. We probably have really flexible hypothesis classes. So if we look at the things we can learn, it's like the style of a new alphabet. It's things like how to use new mechanical devices, like pasta makers and cams. And it's also things like new social gestures that we learn in a new environment. And these are all examples of adult learning. But if you look at what infants do, they're able to do similar things from very few examples, suggesting that the ability to acquire abstract knowledge from very few examples is just basic to human intelligence. Now, obviously, I don't mean to suggest that there's some kind of universal explanation for all of these learning phenomena, but what I suggest is if you zoom in on any one of these, you see an explosive level of complexity and diversity. And so even if we were to focus on mechanical devices or on social gestures, we need radically expressive hypothesis spaces. So within cognitive science, and also within AI in a kind of parallel sense, there's a kind of stock answer to how you might model this, which is that you might have a combinatorial algebraic hypothesis class. There's kind of like atomic elements of hypotheses, and you assemble them like the same way you would assemble an equation or a computer program, kind of a recursive way of doing it. It's like programming your concepts. So this compositional way of assembling concepts can give you very expressive hypothesis classes, but there's a downfall. It comes with a curse. So this is called the curse of compositionality. And roughly, it means that learning becomes incredibly underdetermined and also incredibly intractable. So let's dissect this curse. So first, here is a compositional representation that you're probably familiar with. It's vector algebra. So I can write down all sorts of nice hypotheses. Here's Coulomb's law, and I do this by composing more basic elements. So think of it as like gluing together subroutines. So that's great from the point of expressivity, but if you think of it as a learning problem, it means I take in data, and then I play Maxwell, and I somehow spit out an equation. That's very tough. It's a hard search problem because there are an enormous number of equations, infinitely many, in fact, and only a tiny sliver of them fit the data. And to make our lives worse, that sliver is also infinite, and I want the one that will generalize. So really, there are two curses here. One is that most hypotheses don't work. They don't fit the data. And the other is, paradoxically, too many hypotheses work. And both these things are true, and these are both of our curses. So we're going to try and address these issues. We're going to try and tame these curses using a combination of natural language and Bayesian reasoning. So to understand the way it's going to work, I'm going to introduce a kind of warm-up domain. So this is a classic Bayesian concept learning domain introduced by Josh Tenenbaum like 25 years ago. So in this setup, I give you some examples of a hidden concept. So I'm thinking of some number concept. Here the examples are 16, 8, 2, and 64. And you're supposed to hypothesize what the underlying concept is. And since this is a standard concept, probably many of you think powers of 2. I give you different numbers. Here, like 16, 19, 23, and 20. This is a new concept, which is not one you've seen before. You might think for a while, and eventually convert something like numbers that are around 20. So this is a basic few-shot learning domain, and it turns out it's very rich. There's a whole bunch of concepts you can write down, and it's compositional. I can build infinitely many number concepts. Just like there could be infinitely many social gestures, infinitely many mechanical devices. I have a very rich hypothesis space here, but which is still kind of tractable and easy to think about from a modeling perspective. So the way we're going to model this is we're going to build a Bayesian model. So it's going to use Bayes' rule to try and infer a hypothesis from the data. And that means that instead of estimating a single concept, we're going to construct a posterior distribution over possible concepts. And we're going to attach to each of them a probability which says, how much do I believe that this is the true underlying concept? So this might be a possible posterior distribution for this data. So we're going to have a prior and a likelihood, but more critically, I want to focus on the hypothesis space, because that has to be very flexible. So here are 3 options for that. One is I could use a general purpose language like Python. I could just write down code. I could also design a custom language for number concepts, or I could use natural language. So we're going to step through each of these choices. So if I use a general purpose language, and I want to encode a concept like primes or powers of 2, so the number 7 and the number 64 both being this concept, I could do that. I can write down whatever I want in Python. Python is universal. Maybe I think universal is overkill. It's too hard to deal with computationally. So instead, I design a custom domain-specific language like this. So this is a recursive grammar. It was designed by some researchers led by Pratiksha Thakur about 6 years ago or so. And they were trying to explain how humans can learn all these number concepts. And you can generate kind of syntax trees for concepts like this. And the advantage of this is that inference is tractable. We've restricted our concepts so that we capture lots of interesting kind of number things, but we're not capturing everything you might want to think about. So computationally, easier to deal with. And then we have natural language. So I have literally a string. Obviously, I'm sweeping a lot under the rug here because we have to somehow build into it the ability to understand natural language. But think of it as, it's a string. So here's the downside with domain-specific languages, which is that invariably, whenever we sit down to design them, we forget important concepts. So in this particular paper, there's concepts that are missing, like numbers that begin with a digit. But you could think of other concepts that are missing. And I don't do this to pick on this particular paper. So I spent most of my PhD designing domain-specific languages. And every time I did that, I found that whenever I'd show it to the grad student next to me, they'd say, oh, that's so cool. Can it learn X? And I'd sigh and say, no, I forgot X. And I spent like 6 years doing that. So here's the way to think of this space. So we have things like Python, which are universal, but it's really hard to do inference. Then we have these domain-specific languages, which are customized to like numbers or something like that. And it's a lot easier to come up with algorithms that deal with them, but you're always going to miss concepts that people will find natural and which they will expect that your system can learn. And then we have natural language, which I don't think of as being universal, but I think of it as being domain general. It's applicable to a very broad set of things that humans might think about, but there's certain kinds of things that might be more geometric, or might be better described in algebra or math, which are awkward to do in natural language. So it's not universal in the same way that Python is, but it's going to turn out that it hits a nice sweet spot right now using all this new AI tech, like what Ishita was mentioning earlier. So in the past 3 years, we've gotten these amazing large language models, which can wrangle natural language in ways that were just inconceivable a few years ago. So we're going to exploit those advances and use natural language as a kind of latent representation for Bayesian concept learners. So here's our hypothesis space, going back to the modeling picture. It's going to be natural language. So we're just going to go with that. And that means we have to somehow infer natural language from concrete data. We have to look at some data and say, here's some hypotheses in language that might explain it. The way we're going to do that is by integrating top-down and bottom-up processing. So in a bottom-up way, we're going to propose hypotheses. We're going to do some kind of inference that conjectures things that are plausible and may or may not actually be true, but they're kind of reasonable guesses. It's OK if a lot of those bottom-up proposals are wrong, because it's the top-down process that's going to reanalyze those proposals under probabilistic criteria. So the bottom-up process is going to be a pre-trained language model, and the top-down process is going to be Bayes' rule. So to better understand the connection between the top-down and bottom-up processes, we need to formalize this a little more clearly. So I'm going to draw it as a Bayes net. So there's some natural language. It generates some observed data. And so step one is we need a prior. We need to define the distribution over natural language. The most obvious prior to define distribution over language is a statistical model over language, like a large language model. Now, if you just plug in an autoregressive pre-trained language model as your prior, it has an interesting side effect, which is that longer strings become less likely because they involve more random choices, meaning that simply plugging in a pre-trained autoregressive model gives you something like Occam's razor. You can go one step beyond that. You can also kind of fine-tune the prior to human data, and we'll see that in a few minutes. It gets you a somewhat better fit to the data, but even an out-of-the-box pre-trained model is pretty good because it prefers simpler hypotheses. OK, so the way that the bottom-up process enters the picture is as a kind of inference network or a proposal distribution. So you can think of it as doing something like importance sampling. It generates candidate hypotheses. Those get reweighed. Now, we also need a likelihood, and that likelihood needs to connect informal language to the concrete formal data we're seeing. So something like a link between natural language and numbers. So to do that, as an implementation detail, we're going to convert it into Python. And then we can run the Python code to compare with the observed data. So think of it as like formalizing the informal hypothesis. OK, so this is the basic model. It's kind of like a big importance sampler with language models defining different parts of the graphical model. And now we're going to compare it against humans and see how it is similar and different. So we're, again, working with this warm-up domain, this number game. Here we give humans, so this is data from like 25 years ago. And humans were given numbers like 16, and then asked for a variety of test numbers. For each test number, does it belong to the same concept as 16? And if I just told you 16, you wouldn't know anything. It's pretty underdetermined. So you're basically just guessing. So here, most of the bars are at about a half. Every time you don't see a bar, it means missing data, meaning the humans were not asked about that number. So missing bar does not mean 0. It just means we don't know. So here, humans are confused, but they get less confused if you can multiply powers of 2. They reliably snap onto this concept of powers of 2. And if instead you give them numbers that are kind of in the ballpark of 20, they learn a soft graded concept, like numbers in the vicinity of 20. So you get a kind of smooth decay of these ratings. If you take the basic model I showed you earlier, if you train its prior on human data, then it does a pretty good job of capturing the qualitative features of this simple kind of warm-up domain. Now, we're learning the prior here, and that has something like a few hundred parameters. So that's one of the reasons why it's kind of snapping on so closely to the human data. But what I think is interesting is that if you look at a pre-trained prior, so just the Occam's razor prior, it also does a surprisingly good job of reflecting these human judgments. So now, you might think, well, we're putting a big language model in here. Those are very powerful. Maybe it's a GPT-4 that's doing the work. So you could ask GPT-4 to play the number game, just like humans do. And it does interesting stuff, but doesn't act like a human. OK, so now we're going to look at a richer concept learning domain, where the concept of more logical structure. So this includes propositional logic, which allows you to express stuff like the meaning of the word bachelor, so like male and not married. It allows you to express stuff in first-order logic, like valedictorian, meaning the person within a given school with the highest GPA. Since these are familiar concepts, we want humans to study kind of new concepts. We look at this domain developed by Steve Pantadozzi, where instead of learning about valedictorian and bachelor, you learn about rules involving colored shapes. So to get some intuition about this task, Human subjects are shown shapes in batches, and they're told within a batch which of them obeys the hidden rule. So here they might be told that none of these obey the hidden rule. Here they would then be quizzed on some new shapes, and then they'd be told that the green triangle obeys the hidden rule. And then here they'd be asked, which of these follow the hidden rule? And they probably think, well, I bet the green triangle does because I saw that one earlier. And so they click that one, get some feedback. It repeats for something like 10 or 20 trials. So you can all play this game. It's pretty intuitive, so we'll do it right now. So here I have some hidden concept. You get some set of shapes. Initially you know nothing, so you just guess. You then get feedback. Turns out the yellow ones belong to the concept. Now I give you some new collection of shapes. You have to think what belongs to the concept. We'll do this right now. So I'll just run my finger across these shapes. Please hum when you think something belongs to the concept. It's a lot more fun if you actually do hum. So ready, 3, 2, 1, let's go. All right, so you all did the human thing, but you all got it wrong. Oh, no, actually, you got it right. Oh, wow, you're much smarter than the usual audiences. So actually, most people do not get this after one example. Essentially, that a more cogsci audience snaps onto this a bit quicker. So now we can do this right now, but surprisingly, most of you seem to have already guessed the hypothesis. So we'll do it again. All right, so you're actually the only group that's ever gotten this from one example. So good job. So the rule here was majority color, and you all learned it quite reliably and quite quickly. All right, so we're going to build the same kind of model. It's going to represent stuff in natural language, translate it into code. We're going to have a Bayesian model with a learnable neural prior over language. And we're going to have a large language model that proposes hypotheses, which are rescored under these Bayesian criteria. We're also going to add a kind of memory decay. So stuff that you saw earlier is going to have a smaller weight in the likelihood. So the resulting model does a pretty good job at capturing a lot of fine-grained detail in the human learning curves. So it's an online learning task. We have successive trials. So these all have some hidden logical rule. The language model never actually builds first-order logic expressions. Instead, it's writing stuff down in natural language. And so what you see when you inspect its posterior is it concentrates more and more mass on the right logical rule. Interestingly, it also tends to predict some highly specific learning failures. So here, both humans and the model make a very specific failure on the last trial. And if you look at what's going on, you can get some insight by contrasting the first-order logic with the natural language. So the first-order logic says it is the biggest thing, and it happens to be blue. So it's a little bit of a weird concept. A more similar, more natural concept might be like, well, it's the biggest blue thing. So it turns out that the model has learned it's the biggest blue thing. And humans are acting as though they've also learned that too. So it's not perfect. In general, it actually, on average, slightly underperforms humans. So here's an example of that underperformance. But across over hundreds different concepts, it does a pretty good job at kind of predicting roughly what humans are going to do. And importantly, it's about as sample efficient as people. So here on the x-axis is trials, y-axis is accuracy, and it's a lot more accurate than GPT-4 just on its own. One of our goals here was to be compute efficient, so to not require a lot of inference time to make these judgments. And a proxy for inference time is how many samples do we need to draw from the language model. So like how many draws from our important sampler. And what we see is that we need around like 50 to 100 samples in order to do a good job of explaining the human data. So this suggests that, if you're kind of taking this seriously as some kind of model of what's going on in people's heads, like humans are generating multiple hypotheses, and it's not like 1 or 2 hypotheses, but it's not like 1 or 2 million. Now the model I'm sure can be much more efficient. Probably humans aren't making 100 hypotheses, but we want something which is, kind of a modest amount of compute. So this is driven really by the bottom-up proposals. You could build a similar model that only goes top-down, like sampling from the prior. And that asymptotically with enough samples will converge to the same answer. But in practice, you need many more samples to do that. So we also want a model that's flexible. So just like how you learned majority color, it also should be able to learn stuff like majority color, which involves complicated operations like comparing the size of sets. So we originally started by modeling the Piantodozzi data. We learned a prior from that data. And then we reran new subjects with that learned prior. And we found that it did a reasonably good job at modeling majority color, did a somewhat worse job at modeling minority color, but critically, it was able to learn both these concepts from relatively few examples. Now, if we start with just kind of a standard domain-specific language for first-order logic, unfortunately, it can't actually represent these concepts because it lacks the function for computing set cardinality. So by using natural language, we didn't need to anticipate that humans could think about the size of sets. We just got it for free because we had all the concepts that could be indexed by natural language. So taking a step back, we're putting in this big workhorse of a large language model. We're using, in many cases, GPT-4, which is quite heavyweight. Why do we need to do that? Well, really what it's giving you is a practical way of grappling with the infinitely vast space of concepts using a finite, pretty small amount of compute. So these language models can kind of guess more or less accurately, like where in hypothesis space should you begin sampling. And we're using these as proposal distributions. So large language models are not doing all the work. There's a Bayesian process that intervenes and reweighs things and corrects mistakes. So in the last parts, I'll switch from passive learning to active learning and ask how we could use this framework to kind of propose experiments and answer questions. So this is the new picture here, where the data is used to generate hypotheses, which are used to make experiments. The system does some kind of experiment that makes more data, and we repeat this process. So in everyday cognition, there's examples of this, like when we're playing with a web page and figuring out how to use it, or when we're kind of debugging technical problems. And you see similar stuff in childhood, like exploratory play, or even earlier in life, like in Linda Smith's work, she does lots of active inference and like early visual learning. So in order to build this model, it's really important to have probabilistic beliefs, because we need to make good experiments. So to understand that, imagine that we just had one hypothesis. Like we concentrate all our beliefs on this one hypothesis, and we say, I think this explains the data. That doesn't give you a lot of guidance on what to do next. Should you refute that hypothesis? Should you confirm that hypothesis? It's not really clear. It's much better to have these multiple samples, this posterior, because then you come up with experiments that kind of split hypotheses, where they make different predictions. And therefore, by doing that experiment, you get more information about what the true concept is. So an experiment like this would be good, because it kind of splits H3, the third hypothesis, from the other two. So maybe this experiment will give a positive result on H1 and H2, negative on H3. Therefore, with this experiment, I get some information about what the true concept is. This is also a good experiment. It also kind of splits the hypotheses. The thing, though, is that without some extra probabilities, I can't decide which of these is better. So I really need this full posterior that tells me that, in this case, maybe the third hypothesis is just not very likely. Like, I kind of don't believe that hypothesis anyways. I really believe either H1 or H2. Therefore, the second experiment is the best experiment because it will split those hypotheses. So what we're going to do is we're going to use kind of classic active learning criteria, like maximizing information gain. And we're able to do that because instead of estimating a single hypothesis, instead of just telling the language model, like, what do you think? We do this construction of a posterior. So the second thing that's important is going to be online learning. So previously, we had this kind of setup where all the data went into our model, an important sampler, which generated a bunch of hypotheses. And now, because we're interleaving hypothesis formation with experimentation, we have something like this. So we want something which takes in a little bit of new data, revises the posterior in some little incremental way, and that is used to give the next experiment. So for online inference, we no longer do importance sampling. We do something like sequential Monte Carlo. But just like earlier, we're going to build a sequential Monte Carlo sampler that is guided by a large language model. So the way that works is you have some particles. These are just like samples from your posterior. And this posterior says, you mostly believe the blue hypothesis because it has 3 samples. You kind of don't believe the green one. And the orange one, you're on the fence about. So you use that to make some experiment. And it turns out that experiment falsifies the blue hypothesis. So now we need to update our beliefs. And to do that, we generate some stochastic proposals from a large language model by prompting it with the experiment and the hypotheses. And then the Bayesian mechanics comes in. You reweigh some of these, so some are become much more likely because they kind of explain the new data. Others become much less likely. And then you resample, which effectively kills the low probability hypotheses and upweighs the ones that are more likely. So our new model is going to have these important ingredients we had earlier, but now we're doing online learning with this LLM-guided sequential Monte Carlo, and we're doing these maximizing info gain experiments. One other thing, we found that in modeling human data, it was a lot better to imagine you had kind of fuzzy probabilistic hypotheses. Assuming you have hard all or none rules worked a lot worse for accounting for what humans did. So in terms of what we applied this to, we looked at two setups. So one is these kind of Blicket detector setups. And a Blicket detector is a machine that activates when you put the right things on it. So think of it as like a machine you're trying to discover how it works. So this activated the machine, it played music, you conjecture some hypotheses about why it turned on, why it was making music, and you repeat this process, alternating between experiments and hypothesizing. So Blicket detectors really come from a long series of classic developmental studies. So you basically have kids try to play with a Blicket detector or observe someone using a Blicket detector and then make predictions about what will happen. So, 4-year-olds, they do Blicket detectors. As grown-ups, we also have Blicket detectors. There's a board game which is very similar to this Blicket detector setup called Zendo. So Zendo is a physical board game. You can buy it. You can play it. The grad student who did this work, he's played with a physical Zendo board. And the way it works is you make these Blicket assemblies, and it's more complicated than the one we give to 4-year-olds, but it's the same basic idea. So that was the physical Zendo board. This is kind of Zendo for GPT-4. It's two-dimensional. We describe stuff in text. It's based on this paradigm that was introduced by Neil Bramley a few years back, who's done a lot of work on kind of how humans play Zendo. OK, so if you just look at Zendo, which is kind of the harder version of this, humans are better than just prompting a large language model. So y-axis is accuracy. A model that's quite close to human performance is this online SMC learning of these fuzzy probabilistic rules. If you assume instead the rules are deterministic, you can actually do better than humans, which makes sense because the underlying rules are deterministic, so you have kind of a model mismatch. So you have to make the right assumption. Humans, however, seem to be conjecturing these kind of fuzzy, noisy rules. And overall, in terms of just doing a good job at forming experiments and obtaining beliefs, this online inference is a lot more effective than the importance sampler. So it's better at the actual task. So the resulting model is approximately human level, but we found it wasn't quite human-like. So when we looked at the kind of fine-grained data, it wasn't really a great fit, but it was a much better fit than just asking GPT-4 to play the game. So on the left is just asking GPT-4 to play the game. On the right is this kind of online inference. So we want our systems to be compute efficient, meaning they can't think forever. And humans also can't think forever. So you might expect that as we change the amount of compute, as we give it more particles, more LLM calls, eventually the fit to the human data should degrade because we're kind of overshooting human capacity. And in fact, we actually start to see that. So at the largest compute budget, we see kind of a degradation in the R-squared fit to human data. So taking a step back, there's a collection of kind of lessons for AI and also CogSci that I wanted to leave you with. So one is kind of a way of thinking about the connection between Bayes and large language models. So Bayes give you kind of an algebra for belief, and the algebra gives you these consistent rational beliefs, but Bayes is agnostic about what you're believing about. It doesn't care what the representation is of your hypotheses. It also doesn't care how you do inference. It just says you should do Bayes' rule, and the more you approximate that, the better Bayesian you are. LLMs are very complementary. So they're not very consistent or reliable, but they have this radically expressive hypothesis space, and they are efficient in the sense that they can quickly index this vast infinite space of all natural language concepts. Critically, though, we're using them as proposal distributions. We're not pointing the LLM at the task and saying, do your thing. We're saying, you are part of a graphical model, and you are the inference network. And more broadly, there's a very rich design space of Bayesian models that use proposal distributions guided by these pre-trained neural nets. So in the point of view of humans, it's very hard to model all the stuff you would think with a domain-specific language. At the same time, we have these LLMs that can use natural language to reason and to learn concepts from few examples, but when we actually point them at these tasks, they don't act very much like a person. What we find is that when you combine them with these probabilistic reasoning methods, when you make them kind of explicitly probabilistic, and especially when you learn the prior, they become a much better model of humans. So that's it, and I'll take questions. Thanks.
Time for questions. Oh, perfect. We have, I think, some traveling microphones with our lovely volunteers over here. If anyone has a question, please raise your hand, and they'll run it over to you. We have a question over here.
Thanks for the thanks for the great talk. So this is probably a part that I missed in your talk. So when we are kind of designing experiments in that kind of online setting, to reject some of the hypotheses, like that design of experiment itself is a difficult task to come up with an experiment that can distinguish between hypotheses. Is that done automatically in your framework, or is it something that you think that the set of experiments are given and they can distinguish in different ways? And what is the best one of the experiments to pick from?
So that's a good question. So what I described in the talk was just how we rank the experiments, how we choose which is best. The experiments themselves are generated by the large language model. So it's acting at every stage as a kind of a generator or a proposer. And then there's some kind of re-ranking process.
Got it. Thanks.
Hi. Thanks for the talk. Over here. Hey. I had a question about the baseline, effectively, that we should be using in a case like this. So here we're using a large language model. And what we're finding is that we can replicate how well humans can do these kinds of tasks, the kind of low sample size regime. What do you think the best case scenario is? Because assuming that human beings are also not the best at these tasks, what do you think the best case is? And do you think large language models will just reflect human performance and won't be able to do much better? I'm kind of curious about how you feel about that space.
So certainly you can you can surpass human performance by fine-tuning these models to maximize accuracy. I found that you can't surpass human performance by a lot, at least on these tasks. You can do modestly better. I think more generally, it's hard to really define optimal performance when you're learning concepts that are expressed in Python and in natural language. It makes sense to talk about optimal performance at least least squares regression, but when you have this rich hypothesis base, I can write down all these things that humans can think about. It's not even clear what it means to talk about optimality in a way that's separate from humans.
Hi, Kevin. Great talk. I'm curious to what extent you think that this is a plausible model of how people are actually doing this kind of task, and maybe you could say which parts you think are plausible and which parts you think are less realistic.
So first, one thing that's very implausible is the idea that we have something that was in our head that was trained in the same way that GPT-4 was trained, for example. So obviously, I don't think we have an RLHDEF hypothesis proposer. The idea that we propose hypotheses and then reweigh them out of the data, I think is probably very, very true. The idea that we have a compositional algebraic hypothesis base is maybe a little I don't want to commit as strongly to that, but I think it's also pretty plausible. What I have a hard time defending is that our mental representations are literally natural language. So here, it is literally natural language. And I don't want to make any strong claim that our internal kind of mentalese is the same thing as what we speak with. It might be, it might not be, but there's nothing here which makes that commitment.
Hello, thanks for the talk. I'm Pablo. It was very inspiring, actually. So, but I was wondering, follow up on that question, that tightening reasoning to language means that if you don't have a language, you cannot reason. And this is something that it is easy to falsify. So in your personal view, I mean, we have animals that they can reason without having a language, or maybe they have another type of model of language that is not an LLM. So my question will be, are we tied to technology right now in the LLMs somehow? Or what do you think if we can do some reasoning without language models? Thanks.
I'll answer kind of the engineering and the cognitive version of that question. So from the engineering perspective, are we tied to using large language models to do reasoning? I think in a lot of ways we are. I don't know any other way of dealing with Turing-complete languages or dealing with something that approaches the breadth of concepts that humans can learn, except using an LLM. From the point of view of biological intelligence, you're right, like lots of animals can reason in interesting ways that are very sophisticated. I think language participates in human thinking, but I don't think it's kind of the basis of it. I have not. So hyperparameters like that, which involve rerunning the large language model, we don't tune because it's very expensive, because OpenAI is, they charge a lot. But we should. There's just economic reasons that we don't investigate that.
Hello. Thank you very much for your talk. I think it seems plausible that adults, or we adults here, make use of language to narrow down a hypothesis space. But as you mentioned, infants are particularly impressive in their ability to make inferences. So how could that model maybe be altered to account for that, that step from embodied learning to natural language, or using natural language to narrow down hypothesis spaces?
So that's a great point. I don't think we have the AI tech right now to really do that. I think that if you want to do that, you have to go back to engineering your own kind of custom hypothesis space, which has all sorts of pitfalls. And I don't know how to pre-train something which is like the infant hypothesis space. I think it'd be really interesting to do that. I think it's out of scope and of the work that we're doing here. And infants are a nice example of things that can think without language.
Thanks. It's a really exciting integration of different ways of approaching reasoning. I wonder if you feel you've learned something about the kind of domains in which natural language is a good description for hypotheses or representations. So it strikes me that the examples you looked at are mostly logical concepts, which is something people don't talk about too much at all. So I wonder if there might be other domains where this might be applied and might be even better, like social situations or something like that.
So I think that where this paradigm would really shine is when you have kind of fuzzy concepts that are actually hard to characterize in logic, but where you could write down some kind of sentence and you could ask a language model, is this characterization of the concept a good fit for like this data? So something about the domain-specific languages is they're always kind of these hard logical languages. It's very hard to make like a fuzzy domain-specific language. But if your hypothesis space is natural language, I think you could capture that much better. We haven't done that, but it'd be a nice thing to try.
Hello. Love the talk. Thank you. I've sort of been grappling with this idea of models being used to narrow down hypothesis space and how they sort of roughly get you in the right ballpark. But I also have been trying to figure out why they don't get you all the way, like why we have the Bayesian component that does the correcting, because humans can do both. And so I was wondering if you have any intuitions, like mechanistically, what the difference is in how humans do both of those things and why we're sort of unable to, at least I'm unable to train the models to get to that last step.
No, that's a great question. So one critical thing about humans when they're doing these kinds of tasks is that they can think longer and then do better at the task. And simply prompting a language model does not have that property. There's no sense in which it can think harder. I can't tune a knob, really. Whereas if you have something which is doing a Monte Carlo algorithm with a language model on the inner loop, you can think longer. You can draw more samples. So I think that's really kind of what is going on here. There's a knob, which is how hard do I think? How many samples do I draw? And by coupling Bayes to LLMs, you get that knob.
Thanks for the talk. I'm just curious, could you ask the LLM to generate a task that could break itself, that it could not capture, basically?
I haven't tried that. It'd be interesting. I mean, I think that might actually be very hard because if the LLM puts lots of probability mass on some string with one prompt, it probably puts mass on it with a slightly different prompt. One thing that we have tried is using self-instruct type methods to generate learning problems. And what we found is actually it's usually pretty good at the learning problems that it itself generates. So you probably could do some version of what you're saying, but and it'd be a really cool research question. I suspect the first things that one would try doing that it'd be surprisingly tricky to get it to fool itself.
Thank you.
Yeah, I'm just here, right in front. So humans are usually better at inferring rules when they're in a social context rather than these abstract figures and so on. And I'm just wondering, I mean, basically all the examples that you show were fairly abstract. It's related to as noted by the previous question. But basically behavioral data in humans would suggest that this would change if the rules that you ask them to infer refer to, I don't know, what age people have and whether they can drink or not. So is this something you have tried and to some extent, yeah?
Yes. So in follow-up work, we've been making AI systems that are in some kind of simulated environment. And there's like objects like refrigerators and stuff like that. And they're learning how to use the objects, like kind of the rules of the world. And we do find that by giving it the context, by saying like, you're in a kitchen and you're doing kitchen things, that makes it much easier to generate natural language rules and generate code that describes how the world works. So that extra context helps a lot.